Welcome, class. Today we are going to continue our discussion of aspects of elements. So today we are going to tackle three different topics. We're going to look at the formation of ions, the idea of isotopes, and atomic mass. So let's start first with ions. So as we've learned before, atoms are normally neutral, meaning they have no overall charge, right? This is accomplished by having equal numbers of positively charged protons and negatively charged electrons. So ions, right, are created when atoms lose or gain electrons. So when atoms react, the nucleus is very stable, right? It's kind of a boring part of the atom, right? It doesn't really do much in a chemical reaction at all. But the electrons are where all of the chemistry takes place, right? That's where the action is. And so in a lot of chemical reactions, electrons are either lost or gained. And so ions are created by the loss or gain of electrons. And so an ion essentially is a charged atom, right? Now, there are two different kinds of ions, of course. There are what we call a cation. This is a positive ion. It's a positive charge, and it's created by loss of electrons. So for every electron that is lost, the ion takes on a positive charge. So if we lose one electron, we create an ion that has a positive 1 charge. If we lose 2 electrons, we create one that has a positive 2 charge. Now, sometimes this is a little tricky to understand at the beginning of how by losing negative charge, we end up with a positive charged ion. Well, the way to think about it is the electrons and the protons, right? We start off with a balance of positive and negative. So we have the same number of positive charges as we have negative charges. So if we take one of the negative charges away, now our balance is off, right? We have more positive charge than we have negative charge. So if we lose one negative charge, we end up with having one extra positive charge or a positively 1 charged ion. So that's a cation. Now, an anion is the opposite, right? It is a negative ion. And it is created by the gaining of electrons. So in this case, right, again, we start off equal, but if we gain an extra negative charge, right, we gain an extra electron, then the overall ion takes on a negative charge, right? So if we gain 1 electron, it's a negative 1. We gain 2, it's a negative 2, etc. So we have ions, we have positive ions or cations from the loss of electrons, we have negative ions or anions created by the gaining of electrons. Now, how are these, or what species tend to form these ions? Well, if we look at main group metals, so remember main group, right? Those are the first 2 columns and the last 6 columns. So main group metals will tend to lose electrons. So they like to, of course, form positive charges or positive ions, right, or cations. Main group nonmetals like to do the opposite, right? They will tend to gain electrons. And this allows them to form negative ions or anions. And with both of these, right, they will lose or gain electrons to have the same number of electrons as the nearest noble gas. So remember, noble gases are group 8, right? That last main group. And one of the hallmarks, of course, of noble gases is their stability. Right? And so when other atoms or other elements form these ions, they're doing it to gain stability, right? So when they react and lose and gain electrons, they're becoming more stable. And that's part of that stability comes from the fact that they will end up with the same number of electrons as a noble gas. So again, they'll take on some of that idea of stability associated with the number of electrons that noble gases have. Now, I already talked a little bit about ion charge and how we get this, but just to remind you, right, we can calculate the ion charge, if we will, by taking the number of protons minus the number of electrons. Right? So, if we have equal, of course, it's going to be 0. So if I take a lithium ion, right, and a lithium has 3 protons, and it loses one of the electrons, it takes on a positive 1 charge. So it would be 3, the number of protons, minus the number of electrons now equals positive 1. And so if we look at something like fluorine, right, one of the halogens, right, fluorine starts off in neutral sense with 9 protons. So if it gains 1 electron, then it will have 10 electrons. So minus 10 electrons. So this gives me a negative 1 overall charge. So different ways to think about this. You know, we don't have to do this formula, but this is a way to sort of keep it straight, right? Whether remember that metals like to form positive ions by losing electrons, non-metals like to form negative ions by gaining electrons. We think about the relative number of protons and electrons. That's the bottom line, right? We want to understand what kind of charges these different elements will form. And of course, the overall charge depends on how many electrons are lost and gained. So let's do a little practice here. So let's think about ions and determining the number of electrons, protons, charges, etc. So let's look at a phosphorus ion that has 18 electrons. So if we take a look at the periodic table, right, this is where we're going to go first, right? We're going to look at phosphorus, and we're going to see that phosphorus is atomic number 15, right? So it has 15 protons. Right? So generally speaking, it would also have 15 electrons. But if it has 18 electrons, right, that means it has gained 3 electrons to take on a negative 3 charge. So we end up with a phosphorus with a 3 minus charge. Or if we think about protons minus electrons, if we want to think about it that way, we have 15 protons minus 18 electrons. We get a minus 3 charge. Let's look at the next one. Determine the charge on a zinc ion with 28 electrons. So again, we consult our periodic table, and we see that zinc is atomic number 30. So that means it has 30 protons. So if it has 28 electrons, it has lost 2 of its electrons. from its original 30 electrons. So that's going to give it an overall 2 positive charge, right? We have 2 extra protons from electrons, so we end up with a zinc 2 positive ion. Again, if we want to think about the math this way, we have 30 protons minus 28 electrons, we get a positive 2. And so let's determine the number of protons and electrons in a selenium 2- ion. Well, protons, right, are easy, right? So we need to get in the habit of selenium. Right, we look at the periodic table, its atomic number 34, so we automatically know that it has 34 protons. Now, we know that it has a 2- charge, right? So a 2- charge means that we have 2 extra electrons. So that means we must have 36 electrons. Or if you're more into the equation thing, you could say that the number of electrons equals the charge equals the number of protons plus the charge minus 2, so you get 34 plus a minus 2, or 34, oh sorry, minus, yep, so let's do that again. Wrote that out wrong. So we have minus 2 equals protons plus electrons. So it equals 34 protons minus the number of electrons. And so if I'm going to look at this and I want to solve for the number of electrons, I'm going to say that I'm going to minus, so I'm going to have minus 2 minus 34 equals minus E minus, and so or we can just change that to be 2 plus 34 equals the number of electrons, or 36. So however you want to think about it, right, we need to understand that the negative 2 charge tells me that I have 2 extra electrons here. Alright, so ions. So last thing I want to say about ions is we have to understand some of the basic charges, right? So we talked about how the main group elements have these trends, right, that we can follow. Right? They have predictable properties, and one of those properties is we can predict what kind of charge it's going to form based on its location in the main group, right? So based on what group it's in, we can predict the charge. So, for example, all alkali metals will form positive 1 ions. Alkali earth metals will form positive 2 ions. Halogens will all form negative 1 ions mostly. Group 6, negative 2. Group 5 likes to form negative 3, right? And group 3, like aluminum, likes to form positive 3 ions. So the bottom line is, for these common groups, right, the alkali metals, the alkali earth metals, the halogens, group 6, group 5, and group 3, we want to be able to predict the charge of the ion that's formed based on the group number it's in. So while ions are formed during a chemical reaction, I want to turn our attention now to another topic associated with elements, and that is this concept of what we call isotopes. So isotopes are atoms of an element with different numbers of neutrons. So what isotopes are essentially versions or flavors, if you will, of an element that differ in the number of neutrons in their nucleus. So, when Dalton said back in his original atomic theory that all atoms of a given element are the same, they are mostly the same, but there is one of these differences where there are different isotopes that have slightly different masses. Now, one of the nice things about isotopes is we don't really have to worry about this very often because there's no difference in behavior for the most part in terms of chemical behavior between isotopes, right? All the isotopes of a given element will react the same way, so most of the time we don't even think about what isotopes we have, how much of this isotope, how much of that isotope. The only place where that becomes really relevant is when we talk about radioactivity, which is something we don't really get into in this course. So we want to understand what an isotope is. Now, the other thing that's nice is that the various isotopes of an element always occur in the same percentages. So, for example, we have 3 isotopes of neon. They will always exist in this percentage, right? So there will always be 90.48% neon 20, or 0.27% neon 21, 9.25% neon 22. And that percentage will be the same no matter what sample of neon we have. Now, this is important because these various isotopes will have different masses. So if we want to know the average mass of an atom of an element, right? We want to know how much an atom weighs of an element. We have to be able to rely that this is going to be the same, right? If this changes, then we can't. In one sample, the mass of the element would be this, and it'd be different in a different sample. But we don't have to worry about that because all elements have their unique percent natural abundance, and they always occur in those percentages. Now, there's one other number that we have to think about here, and that is what we call the mass number. Right? So the mass number is simply the sum of protons and neutrons in the nucleus. So it's essentially adding up the number of protons and neutrons in the nucleus, right? It tells me how many particles are in the nucleus. That's the mass number. And that's how we differentiate or identify an isotope. Because they will have different numbers of neutrons, different isotopes will have different mass numbers. So when we were looking at this and we said neon had an isotope, neon 20, neon 20, neon 22, this is the mass number, right? That's how we identify the various isotopes. And you can look, right? They all have 10 protons, right? That's the number of protons that neon has, right? That's its identifier. But they have different numbers of neutrons, so they add up to different mass numbers. Okay? So, isotopes, mass number, and this idea of natural abundance. Now, we saw a little bit the symbolism there. There are actually 2 different ways that we can symbolize an isotope. One is more formal, and that is this one here, where we have the chemical symbol and superscripted on the left is the mass number, right? The mass number is always on top, and on the bottom would be the atomic number. Now, I will say sometimes we leave the atomic number off because we can find it in the periodic table. So you might occasionally see something that would look like that, where they would just have the top number. That's always the mass number, right? The mass number is always going to be bigger than the atomic number. So big number on top, mass number, smaller number, atomic number on the bottom. Now, we put it over on the left, right, because the upper right is reserved for charge, right? If this were an ion, right, we would put the charge on the upper right. Now, the other way to do it a little more simpler is to simply have the chemical symbol or name here. So we can either use neon or write out the name, followed by the mass number. So when you see this kind of notation, right, what they're always telling you is the mass number, right? That's what they have to tell you so that you can identify the isotope. So when we say something like carbon 13, you might be familiar with, right? That's the isotope of carbon that has a mass number of 13. So isotopic symbolism, we want to be able to recognize and write these symbols. So let's do a little practice. So first question says, what is the atomic number, the mass number, and the isotopic symbol for iodine isotope with 74 neutrons? So easy thing first, right? The atomic number, right? And so remember the atomic number is abbreviated Z. If we look up iodine, right, that's 53, right? So it has an atomic number of 53. We have a mass number. Remember, this is abbreviated capital A. It's going to be the number of protons plus the number of neutrons. So we know that's going to be 53 protons plus, in this particular isotope, we have 74 neutrons. So if we add that together, that's 127, right, as our mass number. So we have an atomic number of 53, a mass number of 127, and the symbols, well, we can have two of them, right? We could write it this way, where we have iodine 12753, or we could write it iodine 127, right? Those would be two different symbolisms we could use. Okay, let's look at the next one. So how many protons, electrons, and neutrons are in the phosphorus isotope P33? So the key here is recognizing what they're telling us here. So they're telling us the mass number is 33. So if we look on the periodic table, right, we know that phosphorus always will have 15 protons, right? That's its atomic number. Now, this is a neutral species, right? We're not indicated that it has a charge, so we should also know that it's going to have 15 electrons. Now, neutrons, right, we can get from the mass number, right? So if we know that the mass number is protons plus neutrons, we know that the protons plus the neutrons has to equal 33. So that means 15 plus the number of neutrons has to equal 33. So the number of neutrons equals 33 minus 15, or 18 neutrons. So we have 15 protons, 15 electrons, 18 neutrons in phosphorus 33 isotope. So the last topic that I want to talk about in this chapter sort of starts to pull these things together, and that is what's called the atomic mass. So the atomic mass is the weighted average mass of an element based on the natural abundance of its isotopes. So this is what an average atom of a given element is going to weigh, right? It's a weighted average because we have to take into account the various percentages of the different isotopes, right? Because they have slightly different masses. So we take a weighted average of all of the isotopes utilizing their natural abundance, and that will give me what the average mass of an atom of that element will be. So to calculate this, we take the fraction of the first isotope times its mass. We take we add that to the fraction of the second isotope times its mass, etc. And we do that for however many isotopes they have. So if they have 3, we would do that 3 times. We do it 4 times, etc. Where the fractions of each isotope are those percent natural abundances converted to their decimal values. So in either way, we're going to divide by 100, right? Divide those percentages by 100 to get it back to a decimal. So let's do a quick sample here where we take chlorine, for example. So chlorine has 75.77% of chlorine 35 isotope, which has a mass of 34.97 AMU. We have 24.23% chlorine 37, which has a mass of 36.97 AMU. Now, note that the mass number here, this is important, is not the mass that we're talking about, right? This is not the mass number, this is the mass of the isotope. And those are always going to be slightly different, right? They're not going to be a whole number, right? It's not a count, because those protons and neutrons don't have a mass of exactly 1, right? And there's different effects that go on when all of those particles are put together. And so the masses are always going to be slightly different than the atomic numbers. And these are not things that you would calculate, right? The mass of an individual isotope is not something that you would know, right? These will always be given to you if they're asking you to calculate the atomic mass. So let's lay out this calculation. So following here, we're going to take the fraction of isotope 1. So that's 75.77%. So as a fraction, that's going to be 0.7577. And we're going to times that by the mass of that isotope, which is 34.97 AMUs. We're going to add that to the fraction of the second isotope, right? 0.2423. Oops. Times its mass, right? 36.97 AMUs. So if we do that mass and we get an answer here, we add those together, we get the average atomic mass is 35.45 AMU. Now, notice 4 significant figures because all of the data were given here. The percentages, the masses, all have 4 significant figures. So that's how we're going to end up. Each of these will have 4 significant figures, each calculation. And we add them together. Everything goes at 2 decimal places, so we end up with an atomic mass that looks like that. Now, a couple things to point out here. Notice that the number is quite a bit closer, right, to chlorine 35, right, to the mass of chlorine 35, because notice how much more, right? 3/4, right? 3 out of every 4 atoms are going to have a mass that's close to 35. And so these heavier ones are going to pull it up a little bit, but because there's more of the chlorine 35, your mass is going to be closer to the mass of that isotope, right? That's why it's a weighted average. And of course, notice the units, right? As we mentioned briefly before, right? atomic mass units, or AMUs, is a special unit that we have to express the mass of atoms in, or individual atoms or molecules. And as you might start to realize, right, this is the mass that we see on the periodic table, right? So if we look at chlorine on the periodic table and you look at the mass underneath it, it should be something very close to 35.45, right? So the other number that we're given on the periodic table, we're given the atomic number above, and typically below, we're given the atomic mass, right? The average mass of an atom. Right? And one last sort of interesting sort of thing to think about when we're dealing with this is that to realize that there is no atom in a sample of chlorine that actually has this mass. Right? They all either have a mass of 34.97 or 36.97, but the only way that we can really deal with it is to look at it as an average, because we're not going to be dealing with individual atoms, and so we have mass of this atom, mass of this atom. We have a whole bunch of atoms, so we need to be able to deal with an average mass. And so that's the purpose of these average atomic masses, is so that we can use that in our calculations as the mass of an average particle, even though no actual particle has that exact mass. Okay. So this concludes Chapter 4, and it also concludes our first unit. And so this group of 4 chapters will be what's covered on our first exam, which will be coming up here soon. In our next lecture, we'll be moving on to Chapter 5, but that'll be part of our second unit.